So in this question, it's useful to start by writing out the terms of the sequence that is produced and to try and get a sense of the question. We get these terms where each term is 70% of the previous height. We can see this is a geometric sequence with first term 80 and common ratio 0.7. Now it's tempting to just write here the nth term for this. But note that this is the nth term of the sequence that we're writing down here. It's not the recurrence relation that we're asked for. In a recurrence relation, we need to give each term in relation to the terms preceding it. So it would be un plus 1 equals 0.7 un. There's my recurrence relation. To fully define this, I also need to define my first term here. U1 is 80. So this, for 2 marks, is my recurrence relation. Now be careful in part B. We're looking for the height it will rebound to after the 5th bounce. It's really useful to draw a picture here to get in your head what's happening. So we see on my picture here, I'm dropping it from a height of 80 centimetres. It bounces, and after my first bounce, it reaches 56 centimetres. These blue dots represent my bounces, my first, second, third, fourth and 5th bounce. I can see that my first term of my sequence, 80 centimetres, is before my first bounce. My second term is after my first bounce. Keep working that through and we'll find that my 6th term happens after my 5th bounce. So actually for part B, it's my 6th term that I want. And this is where it was useful to write the information around the geometric progression and the nth term of that, because I'm going to use that now. So I want my 6th term 80 times 0.7 to the 5. That gives me my answer 13.445 or 13.4 to 1 decimal place. What you could do as a double check is we've got our first 4 terms of the sequence here, times by 0.7, times by 0.7 again, and we'll just check we get the same answer. And of course we do. That's my 5th term, there's my 6th term. Okay, now part C is a bit tricky. Find the total vertical distance travelled by the ball before it stops bouncing. We're not given an n, a number of terms, and our assumption here in this kind of model is that actually n could go on forever, and we want the total distance travelled here. This again is where the diagram is helpful. We're looking at this 80 plus 56 plus 56 plus 39.2 plus the other 39.2, the up and the downward journeys, plus 2 lots of that, and so on. So really we're going to start off by looking at the sum to infinity of this sequence and see what that gets us. So the sum to infinity of a GP exists when mod r is less than 1. Well, here r is 0.7, so that's the case, and my formula is a over 1 minus r. So here my sum to infinity is 80 over 1 minus 0.7. That gives me 266.6 recurring. I'm just going to colour on my diagram in green what that represents. And I can think of it as all of these downward distances. Now, if I multiply that by 2, that's going to give me all of my upward distances as well. It will also give me an upward distance of 80. So we're going to times that by 2. So 2 lots of our sum to infinity gives me 533 1/3. but that's going to be 80 centimetres too many. So my answer is 453 1/3 centimetres. Now, in terms of limitations with the model, quite a few of you are mentioning things like air resistance. I think that comes in more if you're talking about parachutists jumping out of planes. When you're talking of dropping a ball from a height of 80 centimetres, the air resistance is probably less so. It's probably quite negligible. So really, when we're looking at limitations of the model here, you can look at the discrepancies between what the mathematical model tells us and real life. So a key thing here is that there's no limitations on n here, and so the assumption is that it could carry on bouncing forever. So that would be our key limitation. And then make sure you write that down in a sentence.